Okay, so when last we met, we had, I think, just gotten to the point where we were talking about the different patterns of resonance. So we have our 5 patterns of resonance that we were highlighting, talking about allylic lone pairs, allylic positive charge. Do we remember what allylic means? What allylic means? What does that mean, Ethan? One atom away from a double bond. Brian, is this what you're looking for? No. There you go. Here you go. Right, 1 atom away from a double bond. So you could have 2 dots on the carbon adjacent to a double bond. Not on a carbon of a double bond, but adjacent to a carbon of a double bond. Or you could have a positive charge 1 carbon away from the double bond. And allylic doesn't only refer to carbon positions. Right, you could be any 1 atom away from a double bond and still be in the quote-unquote allylic position, okay? So things that are in allylic positions, 1 atom away from a double bond, are often involved in resonance structures. What orbitals are involved when we move electrons around in resonance structures? Where do the electrons have to be located? What kinds of orbitals, Luke? Pi bonds or p orbitals. Whether we're talking about electrons that are bonded between 2 carbons or lone pairs, those electrons have to be in the p/pi system. If they're in any kind of an s orbital or any kind of an hybrid involving s character, electrons in those orbitals can't get moved. They are localized. Electrons in s or any kind of s hybrid orbital will be localized and they can't get moved. So we are only moving things associated with the quote-unquote pi system. Okay, so what we're going to do today is we're going to go through one by one different examples of these 5 patterns of resonance. So if you stick to these 5 patterns, and then on a previous slide I showed you like 4 fundamental rules of resonance structures, things like don't violate the octet rule for 2nd row elements. Go beneath the octet rule for 2nd row elements if you must. Make sure you assign formal charges after you move any electrons. So those various 4 fundamental rules, combine that with our 5 patterns of resonance, and you will always be able to draw a good resonance structure. So kind of take the algorithmic approach that we're developing here to drawing resonance structures, and you will never be led astray, okay? I think we finished last time on this slide here where we were looking at the first kind of pattern of resonance structures. And so did I ask you to come up with your own answers to these before we left? I think that's what I might have done. Is that how we ended? Okay, so let's take a look and see what you have come up with in terms of some structures here. So I'm going to zoom in on the guy on the left, the first pattern here. And what did we come up with? Hopefully we came up with something that looks like this. We have our carbon backbone, and we have a double bond there. And then we moved over the lone pairs, so they're right about there. And then we have a negative charge there. Okay, that's not a very good circle. Let me try to draw a better circle. There we go. Okay, so we have a structure that looks like that. I think we probably did this one in class together, right? And we went ahead and we did the red arrow thing. So what we're doing is we're moving these electrons right there, and we're kicking those electrons out to go ahead and generate our resonance structure, okay? All right. What did we come up with for this second one? Let's take a closer look at this one. Let's do the red arrows first. So where will a red arrow begin? Where would the butt of a red arrow be in this case? Where we're going to start?
One of the lone pairs of the oxygen.
Great, one of the lone pairs of the oxygen. Because this lone pair, or either of these lone pairs, where are they with respect to the double bond? What's that name? Allylic, right? So there's the double bond. So we are 1 atom. It happens to be an oxygen this time, right? So it doesn't always have to be a carbon. So we are 1 bond away from that double bond, 1 atom away. So we're going to move these allylic lone pairs. And more specifically, what we'll get to do is we'll take, it doesn't matter which pair you pick, just pick one of the pairs, shove them into that carbon-oxygen bond. And then what do we have to do as a result? We have to move one more set of electrons, right? Because if I stop here, what's the mistake I've made? If I stop here, yeah, I've got 5 bonds to carbon. I've got 10 electrons to carbon. So I've got to complete the process and kick out some more electrons, right? Moving of allylic lone pairs will always be a 2-arrow move. Every time I move allylic lone pairs, it's going to be a double arrow move. Otherwise, I'm going to violate somebody's octet rule, and I don't want to be doing that, obviously, okay? All right, so then let's draw the resulting structure that we get out of this. Okay, so we're going to have, let me shrink this down a little bit. So let's see, we're going to have our oxygen, and then we have a new double bond, then we have a new single bond, single bond, single bond. I get a couple of lone pair electrons there. I get a couple of lone pair electrons there, and I've got a negative charge there and a positive charge there, right? So don't forget about completing the structure with the formal charges. The most common mistake I will see, I think, is not accounting for any newly developed formal charges after we move the electrons, okay? All right, so one more move then. We've got to take a look at this last structure on the far right. What kind of a functional group is this guy here on the far right? What are we looking at here? What kind of a functional group do we have there, Trace? We have an amide, an amide or an amide. You can, I've heard it pronounced both ways, so amide or amide, wherever you want to put the emphasis on whatever syllable you want to do it, okay? You can get amide or amide, okay? Now, where is the allylic lone pair? Which atom is holding the allylic lone pair? Who has it, Matthew? The nitrogen has the allylic lone pair. There's our double bond. One atom away, we have a nitrogen, and it's got some lone pairs on it. Now, if you saw this structure, right, if you saw that nitrogen, and this was sophomore year chemistry, and you were asked, hey, what's the hybridization of that there nitrogen? What would you have said sophomore year? And I'm not trying to suggest that you were wrong sophomore year. I just want to go back in time, right? What would you have said about the hybridization of that there nitrogen about, what, 6 months ago? What would you have said? What would you have said? You would say 100%, you would say sp3, because it's a nitrogen, and it's got four occupied areas, right? 1, 2, 3 bonds, and a lone pair. You would call that 4 occupied areas. So you would think that is sp3. That's what you would have called it. But what did I say to start this morning about where the electrons need to be in order for them to be able to resonate? They have to be in the pi system, or the p orbitals. So if we think that those lone pairs right there, if we say, hey, those are in an sp3 orbital, they will not be able to resonate. So it turns out that the structure of amides is a little bit interesting, okay? What we might normally convict as an sp3 nitrogen, that nitrogen is actually sp2 hybridized. And the lone pair, they're in the unhybridized p orbital. That way they can communicate with the pi bond that's adjacent to them, all right? So the evidence suggests that these lone pairs do resonate. Experimental evidence suggests that this carbon-nitrogen bond will occasionally have some double bond characteristics. And the only way that could happen is if you do some resonance. So this nitrogen is probably best described as being sp2 hybridized, with the unused p orbital being the location of the electrons, okay? So this is where resonance starts to complicate things a little bit. So, given now that maybe it is indeed sp2 hybridized, we can now resonate those electrons, and maybe we would draw arrows that look like this. We'd have the electrons from the nitrogen go into the carbon-nitrogen bond, and then of course I can't stop here because I would be violating the octet rule, and moving allylic lone pairs is a 2-arrow move, so I kick out those electrons and put them out onto the oxygen. And so the net result I would have there would be a new structure that looks something like this. I'd have my oxygen singly bonded to the carbon, then I'd have a double bond to the nitrogen with its two methyl groups on it. And don't forget, I've got that other carbon there. And then I've got some more lone pairs. I can put the original two on the oxygen, and then I've got a third set now of lone pairs on the oxygen.
What would the bond names on the nitrogen be?
So they would be mostly sp2. They would look mostly like sp2, so that nitrogen you would expect would be trigonal planar, and you'd have 120 degrees. Now that lone pair that's sitting in that unused p orbital probably is going to cause some deformation from perfect planarity. Is that a word? Perfect planarity and perfect 120. So it's probably not the world's most idealized platonic representation of a trigonal planar structure. Brian?
Isn't the oxygen partially negative?
Yep, I'm glad you picked up on that as we interrupted ourselves. Yep, thanks for the reminder. So the oxygen has definitely got a negative formal charge on it. What else? The nitrogen, right? That nitrogen now only has 4 bonds going to it. So it is low on electron density, so that nitrogen must have a positive formal charge. Okay? Don't forget to put in your formal charges after you move allylic lone pairs. Okay? All right, so that's the allylic lone pair move. Right? It's a 2-electron move. All right, and you've got to watch out for the creation of formal charge. All right, take a look at another move here. The movement of allylic positive charge. So it looks like we're going to be moving the positive charge, but we don't move positive things. What are we actually moving, of course? The electrons, right? So the consequence of moving the electrons will generate the movement of the positive charge. Okay, so I've got 2 things going on in this structure. I have here an allylic positive charge. I have a positive charge, 1 atom away from a double bond. What else do I have going on? In purple, conjugated. What does conjugated mean again? We saw this word towards the end of last class. What does conjugated mean, Ethan?
It alternates between a single, double.
Great. So we have a double bond and a single bond, a double bond and a single bond. So if you have alternating double and single bonds, that creates a structure referred to as conjugation. All right? And what it's going to do, conjugation tends to generate multiple resonance structures. Not just one other good alternative, but probably multiple good alternatives. So let's zero in then on my structure here so I can draw in the red arrows. So I will have what gets actually moved. Where's the butt of my arrow going to start specifically? Which electrons? Can it start, say, on these electrons? Could I start there? If I started my butt of my arrow there, what cardinal sin would I commit if I tried to move those electrons? It was like rule number 1 of what you don't do. What was it, Matthew?
You would break a bond.
I would break a bond. I don't want to break a bond, right? If I break a bond, I'm doing something other than generating resonance structures. So let's not break that bond. So what we're really going to do then is go after the double bond that's here and move those electrons over, okay? So I'm moving the electrons from the double bond over to the carbon-carbon single bond. Because that positive charge, right, this carbon right here that I just circled, the one with the positive charge, what's its hybridization? Because it's a carbocation, what is its hybridization? What is it? It's sp2. So there's a p orbital right there on that circled carbon that's empty, that's saying, I'd love to get some electrons. And so the pi bond, 1 bond away, can slide over and create the next resonance structure. Okay, so then to the right of that arrow, go ahead in your notes, go ahead and write the resonance structure. What do you think it's going to look like? Give yourself 20 seconds to draw what happens after I do the red arrow move there. What's going to happen? So we got 2, 3, 4, 5, 6. All right, so I have my 6-carbon chain. I moved the double bond over, so now the double bond is there. I haven't touched the other double bond, so that's still there. And what do I now have to put in? A formal charge. And where is it located? It's right there on that carbon right there. Okay, so I've moved the allylic positive charge by way of moving the double bond. Is there another resonance structure? Yeah, obviously there is. So I could then go ahead and move the next set of double bonds, the next pair of electrons in that double bond, move that over, and I can create a third resonance structure. I'll just go ahead and draw it down here. So 2, 3, oops, come on, pen. So 2, 3, 4, 5, 6. My double bond on the end, my double bond is moved over, and I have my allylic positive charge now on the end. Okay? Let's do one more thing with this. Go ahead and draw for me. What am I going to ask you to do next? There's no more resonance structures, but there's one more kind of a structure associated with resonance that I could ask you to draw. What could I ask you to draw next? Remember nectarines? My conversation about nectarines. What am I about to ask you to draw? The resonance hybrid. Okay. Draw for me the resonance hybrid that is sort of the overall average, as it were, of these 3 resonance structures. Okay, the resonance hybrid is what we're looking for here. What is our resonant hybrid? 2, 3, 4, 5, 6. Draw this in black. We're looking for the resonance hybrid. Remember, this is the thing you do dash, dash, dash to represent any bond that spends any time doubly bonded. And then don't forget to put in your pseudos. All right, so let's go left to right. The first carbon-carbon bond on the far left to the second from the left. Does that spend any time doubly bonded? Sure does, so we'll put a dash, dash, dash there. How about the next bond axis between carbon 2 and carbon 3, let's call it? Does that spend any time doubly bonded? Yeah, it was the original double bond, so we can put some dash, dash, dash there. How about the third axis between carbon 3 and carbon 4? Yeah, it sure did, so dash, dash, dash. How about the next carbon axis? Yep, dash, dash, dash. And how about the last, from carbon 5 to carbon 6? Nope, so there's the end of my dash, dash, dashing. Who gets a pseudo-positive charge? Does carbon number 1, the one on the far left, does it get a positive charge? Yes, it did spend some time, so let's put a delta plus there. How about carbon 2? No, carbon 2 never had a positive charge on it. But carbon 3 did, so I'll put a delta plus on carbon 3. Carbon 4 never spent any time as positive, but carbon 5 did, so we'll put a pseudo-positive on carbon 5. So then, let's say you're going to do some chemistry. Maybe you are some X thing that's anionic. Now you can predict where that X is most likely to go. It's most likely to go either here on the first carbon, here on the third carbon, or here on the 5th carbon. You would be kind of surprised if this X minus ever formed a bond with, say, carbon 4 or carbon 2. You'd be flabbergasted if it did anything to carbon 6. Okay? Nothing's going on there at carbon 6. So resonance structures are a way to begin to crack open the nut, open up the can of reactivity. By drawing different resonance structures, we might have a hint where the electrons like to spend their time, and as a result, how something that's got some positive charge might react with something that has some negative charge. Okay? All right. So that is then allylic positive charge. Who's next? Allylic lone pairs, allylic positive charge, and a little bit about conjugation. What was the third pattern of resonance? A lone pair adjacent to a positive charge. Was that what? I think that's what was next, okay? These are pretty straightforward, right? These are going to be pretty obvious. You're going to have an atom that has lone pairs and itself might also be anionic, and it's going to be immediately adjacent to an atom that has a positive charge. So anytime you have a lone pair immediately adjacent to a positive charge, that's screaming to be moved. What kind of a functional group is featured in this first pair of resonance structures? That's a ketone. Very good. That's a ketone. So if you start with a ketone, you can generate this, but let's start with the one that has the separated formal charges. So I have lone pairs adjacent to a positive formal charge. Again, what is the hybridization of that carbocationic carbon that I'm pointing to? It's sp2. So it's got an empty p orbital that is ready and willing to receive electron density. So I can turn one of the lone pairs on that oxygen through a simple one curved arrow move to create a new carbon-oxygen double bond, just moving electrons from a p orbital here over onto the p orbital that's empty on the adjacent carbon and create a new carbon-oxygen double bond. Okay? Now, the source of the electrons doesn't always have to be anionic. I don't need a negative charge there because I could play around with a structure that looks like this. What kind of a functional group am I generally playing around with here in this starting molecule on the left? Functional group. What is this? Begins with E. Yeah, ether. Very good. That's an ether. So ethers have lone pairs on the oxygen. Notice that oxygen is not anionic. So it's not like jonesing to give up the electrons, but it's more than willing to do it to a neighboring cationic carbon. So we can take those lone pairs and we can move them over into the empty p orbital on the adjacent carbon. All right, and then I get this ether that has a double bond in it, so things are starting to get complicated. And of course, the oxygen, as a result, now has a cationic +1 formal charge. Okay, so that's our third move. This one's usually pretty obvious, right? And it's not dissimilar to what goes on with that allylic positive charge. You have a positive charge in the molecule, so try to get some electrons towards it to satisfy it, right? A positive charge is a telltale sign for the movement of electrons, okay? Should be expected. All right, next move we could do. This is sort of the opposite of the one we just did. If you have a pi bond between two atoms of different electronegativities, then you're set up to do our fourth move, which is move the electrons from the pi bond out to a lone pair on the more electronegative atom. So we have this structure here. We have a simple ketone, and this is exactly the opposite of what we did on the previous slide. Start with the neutral ketone, move the pi bond out to the lone pair on the oxygen, and you generate that doubly formally charged structure there. And of course, this structure is just going to want to go back and do the lone pair back into the pi system to satisfy that carbocation. All right, so this is just a back and forth, a yin and yang, a seesaw, a tug of war between pattern 3 and pattern 4 here. All right, and then what's this functional group? What's that functional group? it is acceptable that you are utterly silent here because this one we didn't see. This is not one of the 16 common functional groups that was on the sheet I gave you. But this guy is called an imine. Take amine and change the A to an I. It's an imine is what it's called. Imine, I-M-I-N-E. That's an imine, okay? What move can we do with this here imine? What could we do? What's my red arrow going to look like here? It's going to start here on the double bond, and it's going to go out to the nitrogen, right? The carbon-nitrogen bond is not terribly polar, but there is an electronegativity difference there to be sure. So I could then generate the following resonance structure out of this, right? I could have my nitrogen at the top, still has that carbon bonded to it. Now it's got one lone pair, two lone pairs, a single bond to the other two carbons, and I'm done. I'm not done. What have I forgotten to do? Formal charges, of course. So I'll have a positive formal charge on my carbon, and then the nitrogen we have here, let's count it up. I have four electrons from the two sets of lone pairs, 5, 6, so I've got 6 electrons around that. So that is, of course, going to be then a -1 formal charge there. Oh, that circle is terrible. There we go, that's a little better. All right, so then I have, this is sort of a kissing cousin of something like a ketone, where you're just moving from a double bond out to the more electronegative atom. It's sort of a kissing cousin of that move. Yeah?
That's an imine. Wouldn't imide be like an oxygen?
Say that again?
If that's an imine, would there be like an imide?
Well, it's an imine.
Imine.
Okay, we don't call it an imine. That's not a long I. It's an imine. But what do you want to rename?
Like, if you add an oxygen,
Uh-huh.
like do the same transfer like from an amine to an amide?
From an amine to an amide. Okay, I'm trying to figure out what kind of a structure you're thinking of there.
Like replace that with an oxygen.
Oh, okay, so put an oxygen in place of that nitrogen.
No, replace it with the carbon. With the double bond?
Okay,
Yeah.
put another nitrogen on that carbon.
An oxygen.
Oh, an oxygen, you want to put an oxygen there?
Yeah.
Oh, never seen anything like that. Yeah, you're going to run into, let's see, that nitrogen-oxygen bond. Ooh, that doesn't strike me as going to be terribly stable. But yeah, I don't think I've ever seen a structure like that. The folks who name all these kinds of compounds, the folks in charge of nomenclature in chemistry, they are part of what is referred to as the International Union of Pure and Applied Chemistry, IUPAC. Okay, these guys are like hardcore party animals because they spend their time naming compounds. And what could be more exciting than naming compounds, right? Somebody invents a new compound, right? It has a systemic name. It has a systematic, formal name. And if it's a really complicated compound, like on 1.6, on that next set of problem sets I gave you, look at the structure on number 2, okay? That thing has an official IUPAC name. If you were to like write it out by hand, it would like take a couple of lines to write out. It's like very, very long, and it's got all sorts of numbers and interesting symbols in it. But somebody had to come up with a systemic way to name that thing, and it's been done. You know, you just can't call it, you know, George. There's got to be a systemic way to name it. So, the party animals at IUPAC. All right, let's see. Do we have any other patterns left? Are we done? We got one more. What's our last one? Yeah, more conjugation, right? Our last one has more to do with conjugation. So this is playing around with the alternating carbon single and double bonds in a ring. So we saw conjugation with respect to a allylic positive charge. Here's conjugation, no positive charge, but inside of a ring. What functional group are we looking at? aromatic, of course, right? This is the aromatic functional group that we're looking at. So we have our alternating double and single bonds here. So the reason we can do all these arrow moves is every single carbon in this structure, oh, that worked out really well. Did you see what I did there? Every single carbon in this structure, I didn't realize there were going to be 6 words in that sentence, but it worked out perfectly, actually, in that dependent clause. Every single carbon in this structure is what hybridized? It's sp2 hybridized. So these electrons are just spinning around like a merry-go-round. Around and around they go. Okay? This kind of a resonance structure, when you have conjugation inside of a ring, is going to be a multiple arrow move. This is a 3-arrow move for this particular 6-carbon aromatic compound. Every aromatic compound we've seen has been this example of a hexagon, has been this 6-carbon ring, but other sized rings can be aromatic. You just need this sort of alternating pattern. So it is possible to have aromaticity within something other than 6 carbons and something other than a hexagon, okay? And it doesn't matter which way the electrons move. I have them moving which way here? Counterclockwise. You can show them going the other way. It really doesn't matter, okay? So what's the, draw for me the hybrid of this structure. What's the resonance hybrid look like for this guy? So I've got 1, 2, 3, 4, 5, 6. So I have a hexagon. And what's true about every single carbon-carbon bond? They're all going to spend some time as a dash, dash, dash. So you can draw things in dash, 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 but the other convention that's used in this particular case is to just draw a circle in the middle of the thing. Just a circle, not something with a nose in it. Just a circle in the middle, okay? And hopefully you can draw a better circle than I can. Let me try it with my finger. Let's see if I can get a better circle with my finger. Mildly better. Okay, you get it. Should be a circle in there. So this is the molecule benzene. You will see it sometimes drawn with the alternating bonds, thusly, or sometimes just with a circle in the middle to kind of emphasize the aromatic nature of what's going on. Okay? So we have 4 fundamental rules associated with drawing good resonance structures. And then we have our 5 patterns. The 5 patterns are summarized on the last slide, or the second to last slide we're going to talk about today. All right? You'll notice how this nicely articulates the number of arrows you need, so that allylic lone pair, that's a 2-arrow move, allylic positive charge, lone pair adjacent to a positive charge, pi bond between atoms of different electronegativities. Those are all 1-electron moves, nicely. And then the movement of aromatic conjugation inside of something like benzene is going to be a multi-arrow move. In this case, it's a 3-arrow move. So if you keep this chart, and again, those 4 rules of resonance structures, don't ever violate the 4 rules as you try to pull off one of these 5 moves, and you'll always generate good resonance structures, okay? Now, our next step after this is to evaluate the quality of our resonance structures. We can draw valid resonance structures with our patterns and rules, but not all resonance structures, as we will see, are created equal. Some are better than others, okay? So we ultimately are going to care most about the best resonance structures. That's the next level of our conversation. But from here on out, here's what we can do. Here's a fun-looking molecule. This thing has all sorts of functional groups in it. How many resonance structures can you come up with this guy? Abiding by the 4 rules and applying the 5 patterns to as many different portions of this molecule as you can. See how many resonance structures you can come up with. I'll give you a hint. It's more than 2, but it's going to be less than 8. I didn't say exactly in between. So there's multiple resonance structures here. I don't think it's 8. I don't think so. All right. And I've included one little hint down here at the bottom. Okay? Hint. Carbons with 4 bonds that are sp3 hybridized isolate areas of resonance from each other. So, for example, this carbon right there, that carbon is sp3 hybridized, okay? That carbon is essentially like a boundary condition. It's a roadblock. In other words, anything that might go on around this part of the molecule or anything up here in this part of the molecule, because of the presence of that sp3 carbon, it won't be able to get to this part of the molecule. So this double bond that I'm pointing to right now will not be able to get over here. The electrons that are in that double bond will never be able to get over there because that sp3 carbon does not participate in any empty p orbitals or anything like that. So there's no way to communicate any of the electrons here to over here. Same thing for this sp3 carbon. All right, so be on the lookout for sp3 carbons. They're kind of boundary conditions on the kinds of resonance structures you might be able to do. So really what we've got here is kind of one isolated area and then 2 areas that may not be isolated. So play around with the different resonance structures you might be able to generate from here. And do the arrows first. And keep it simple, silly. Draw one kind of an arrow, okay? Draw a single arrow denoting electrons adjacent to a positive charge, then draw that structure. Don't draw something that's got like 6 arrows in it and then see what you get out of it. Keep it simple, silly, for now, and see what you come up with, all right? So we've got about 10 minutes left, so work on this fun-filled example, or if you want to start looking at 1.6, either tact is good at this point, okay?